name is, my name is, my name is Weezy Baby and I'm high. My name is, my name is, my name is Weezy Baby and I'm high. My name is, my name is.
For our project, we implemented the engineering design process. It has 5 steps: ask, imagine, plan, create, and improve. We chose the fountain project, with constraints including a $40 budget and a 2-foot by 2-foot space. There are many different aspects to fountains across the world. However, we cannot put all of them into one, and so we decided on laminar flow. Laminar flow seeks to get all the water within a pipe moving in the same direction or parallel to one another. This is opposed to turbulent flow. This makes the water coming out of the nozzle appear almost frozen.
The third step of the engineering design cycle is plan, and part of this step is drawing a diagram and gathering the materials needed to follow through with your plan for your project.
Our first challenge was figuring out how powerful our pump had to be. We figured this out by researching equations that describe fluid dynamics and basing the equations by how tall and far we wanted to shoot the stream of water.
We decided to use Autodesk Inventor to draw a diagram that would end up being a 3D model for our laminar nozzle. We also needed to require the needed materials for this, and initially we definitely knew we were going to need 3D printing filament, so that's the first thing that we got. We also knew that we would need some sort of sealant or caulk.
A few other materials we needed included straws, some plastic clear tubing, the Scotch-Brites, some wooden dowels, screen to hold in the straws within the laminar flow nozzle, and last but not least, of course, our pump, which was rated at 370 gallons per hour, which was a little more than what we needed, but it had an adjustment to where we could turn it down and make it exact. Traditionally, the laminar flow fountains are very bulky, so we wanted to try to slim that down a little bit and make it more professional by utilizing 3D printing. This is one design for a laminar flow jet. As you can see, it utilizes the Scotch-Brites to dissipate the water evenly, and then it uses the straw segments to get the water all flowing in the same direction, which will eventually get you that nice stream of water we're aiming for.
The first model we tried to design on Inventor had the parallel holes that are required for laminar flow integrated into the 3D model instead of using straws or coffee stirrers like is usually done to create a laminar nozzle. Once we did the test print for our first idea for the laminar nozzle, we realized that our design was not really going to work because the 3D print failed and one of the pieces that we had actually came off, as you can see in this picture. One thing that happened was we realized that the built-in laminar nozzle holes were not going to really work because it was likely that they weren't going to be smooth enough to ensure that all the water ran parallel enough and smooth enough to ensure that we would get a nice laminar flow coming out of the top of the nozzle. We ended up having to redesign the nozzle several times just due to the number of things that we realized were not going to work.
Once we removed the straws, we kept the circular pattern, but quickly realized that that was not going to work either because we didn't have a way to really fasten all of our different parts together.
In these pictures, you'll notice that our laminar nozzle is made of several different pieces. We had to 3D print it into separate pieces because the entire entity could not be printed as one piece due to the way the 3D printer functions. The first piece had a hole built into it so that the tubing carrying the water could connect to the nozzle. The second piece essentially was just a piece the same shape as the nozzle with a hole in the center of it, a cylindrical hole about 1.5 inches wide. This is the piece that we stuffed the coffee stirrers, the mesh screen, and the Brillo pad in order to create the actual laminar flow.
We held the entire assembly together using 1/4-inch bolts.
The fourth piece was essentially just a flat piece that was maybe 1/8 of an inch thick and had a hole in the center of it. This hole is where the water came out in the laminar stream.
Initially, our flow wasn't very laminar. We thought this was because the nozzle was neither big enough nor sharp enough. So we printed a bigger nozzle and drilled a hole through aluminum metal and attached that to the nozzle. That allowed us to create a sharp edge. Our last challenge was attaching the nozzles to the fountain itself.
This was difficult because it is hard to bond plastic and metal.
We were able to use epoxy glue for this.
As you can see, we had somewhat of an on-site failure as far as the epoxy goes, and so we had to make some slight on-site adjustments with the duct tape.
We didn't realize how crazy the makerspace would get this time of year. We should have 3D printed earlier before it got too busy. This would have allowed us more time to focus on the aesthetics of our project, rather than the laminar flow aspect. While the laminar flow is what we're most proud of, the judges seem to consider the aesthetics of each project most.
The most difficult parts of our project were the time and money constraints. Because of this, our team's advice to future participants in the project would be to design your project realistically. Our team had many ideas that we wanted to incorporate into our fountain, like an infinity pool and laminar flow, but the constraints that we had made it extremely difficult to achieve what we wanted the fountain to do. We spent most of our time dealing with the logistics of making laminar flow, that we neglected many design aspects until the very end, causing our fountain to look messy and rushed, even though the laminar flow worked pretty well. Overall, manage your time wisely and be realistic about your limitations and designs for the project.